Thank you. So first, it's the Faculty of Computer Information Science. We merged recently with the Computer Science Department in our university. And this research was done in the Cybersecurity Research Center of Ben-Gurion by a student, Emmanuel Goldberg. Actually, very neat and interesting, surprising application that was presented as a poster in IEEE Security and Privacy this year. My group in this research center deals with cyber physical security, cyber biological security, and actually the psychology of AI models, psychological traits of AI. Very interesting topic. Here, I would like to talk about the cyber physical part. And in the cyber physical systems, you have the cyber and the physical. In the physical, you have actuators, you have the actual machinery that is working, things that do affect our physical reality and are guided by physical rules, by physics, like Kirchhoff rules or liquid viscosity or whatever. And we have some sensors to know what is going on there. On the cyber, on the digital part, you have the control logic, you have the software, you have the communication. You have all these parts affecting or trying to understand what goes on in the physics and trying to affect it. And actually, the relationships between them are quite convoluted, both to protect the cyber physical systems and to attack them. Attacker needs to understand what goes on in the physics to make the highest impact. People involved in both also usually not speaking the same language, but that's already a different goal. So what goes on usually? You have the sensors in the physical realm that transmit measurements to the digital realm. And those, the control and the software understand what goes on in the physics and transmit commands to the actuators that affect the reality. When we talk about attacks in the cyber physical domain, it's usually quite similar. The attacker would like to make the highest impact by slightly modifying the commands that the control logic is transmitting, and he would like these adversarial manipulations to remain undetected. So he would like the stealth, the attacks to be stealthy, and the sensors not detect the anomalies caused by the attacks. But actually, it's much wider than that. The relationships between digital and physical and the spillover from the digital ground to the physical ground and vice versa. If we talk about physical to digital, the easiest thing to grasp is tampering. Physically tampering with a device has effects on the digital reality, has effects on the software and so on. You plug in a USB, you affect the software. You disconnect the cable, you affect the communication. So you have physical tampering with digital reality. Digital to physical is the most traditional cyber physical attacks that we know. You have the malicious software trying to manipulate the physical realm and the physical processes. And then you have some indirect relationships between the physical and the digital realms. For example, data leakage. You can use side channels and you could use the physical laws to leak information from software into the environment. And the most interesting thing that is least researched, at least as far as we saw it, is the spillover from the physical to digital through the environment. So what manipulations can you do in the physical realm to affect the behavior of the software in a malicious way? There are a couple of related work in this area. There was one very interesting work in 2017 in Unix that created a DNA molecule, actual physical DNA molecule, that could exploit a buffer overflow in a DNA sequencer. So, what could ever go wrong if we manipulate the environment? How could the computers be affected? How can the communication be affected? That's the question. So, in order to understand what can be done, first, we need sensors. So, every information that comes from the physical realm comes into the digital realm by sensing. So, let's get the most known sensing device, the camera. Okay, that's the easiest one. Everyone knows it. It takes the physical world, translates it into pixels, and transmits the communication. So what's most interesting for us about the cameras? Today, cameras produce huge amounts of data. And in order to make it tractable and in order to not overflow the communication network, they have compression, and compression rates are very high. A compression ratio can range from 50 to 300 and even more in static scenes. Compression ratio is affected by the scene complexity, it's affected by the motion, it's affected by noise, it's affected by color variation and light conditions, and so on. Even one of the very important parts of the codecs that do video compression is motion prediction. So if you have a person going through the corridor, it does not affect the compression ratio that much because they know where the pixels move in the frame, they predict it, they encode it in the compressed data. So these video codecs can be exploited, can be manipulated. This is actually a very interesting work. A few years ago, also done in our lab by Ben Nassi, they wanted to understand whether the drone is looking at some particular area. So what they did, they manipulated the scene, and only by flickering the window shades here, they could cause an IP camera of a drone to increase the bitrate by 20-30%, a detectable thing. And they have used it in order to understand whether the drone is looking at something. Now what we are doing, we would like to take it to the extreme. Okay, so we would like to manipulate the scene in such a way that the bitrate doesn't go 20% up. It goes 600%. So we would like to manipulate the compression ratio of IP camera and use them as an attack tool for ourselves. Or at least try to do so and understand what are the consequences. Is it possible? So what we use for that, this custom-made device with a single laser beam and some things that do noisy, add some noise to the laser. The most interesting thing about this attack is purely physical. No digital footprint at all. So you turn a camera into an attack agent without having any digital footprint, any digital touching of the IP camera. You have no software, you have no exploits, you have no vulnerabilities, nothing. Just manipulation of the compression ratio. It's indirect. You manipulate the physical environment using a laser beam, and you have the digital spillover, so the camera produces huge amounts of traffic. And the results show that we can generate up to 6 times more traffic using a laser beam. When tested on wired and wireless networks, it shows elevated jitter, latency, even packet loss in many cases. So if you would like a single slide to summarize this entire talk, this is the slide. So when you point a laser to a camera, this is what camera sees. You see the stripes. The stripes come because of the scanning of the camera. It's progressive scanning. Camera does not take all pixels at a time. It takes 1 pixel at a time. So that by the time it reaches these pixels, the laser have flickered on, off, and so on. So the flickering rate is quite high. This produces a very noisy, unpredictable pattern. So pre-motion prediction doesn't work here. You have high contrast here. You have dark and light areas. You have variety of pixels that are very tough, very difficult to compress using existing algorithms. Okay, so let's see how it works. Let's see what it causes. Of course, the best way is to point the laser directly at the camera eye. It's not possible. It's not always possible. And the effect of these attacks depend on the incidence angle. It less depends on the horizontal angle. So you see as the laser beam shifts toward the sides, the effect of the attack reduces. An interesting effect we saw on the vertical axis, up to 40% of that particular camera, 40 degrees, sorry, of that particular camera, there was no effect, but at 45, the laser already did not have any effect. Probably due to the glasses of the camera itself. Okay, so you have the camera. You can increase the bitrate of the camera. So what? So now we built a network, a testing environment. This is an example of a wired setup. We have a similar wireless setup with many different adapters. The wireless setup was flat. The wired setup has one physical switch employed, and the rest of the machines were virtual. There was background traffic created in order to load the network up to roughly 80-85%, and to see what happens when you generate excess traffic with the IP cameras. So in a 10 megabit per second Ethernet cable with somewhat 83 megabits base load, when you activate the laser, you get very high increase in the latency, and you have packet drops here. On the x-axis, you can see the packet sizes of the base load. So if the background traffic transmitted in the network uses large packets, of course, the effect is higher. You have more packet drops, you have a higher latency. In any case, the packet size results in the same base load. So if the packets are bigger, there are fewer packets. A very interesting effect was seen at the wireless setup. 22 megabits per second was roughly creating a similar load, but in the wireless setup, we suddenly saw a very elevated packet drop rates with small packets. we understood that this is not due to overloading the channel itself, but because of overloading the queue of the wireless router. So overall, you have you can cause spikes in the traffic by pointing a laser into an IP camera. This can create latency, increased latency. This can create occasional packet loss, especially when the network itself is already loaded. In certain systems, in certain critical infrastructures, these sudden spikes may be very damaging, very bad. In offshore oil rigs, they can even cause evacuation of the entire oil rig if the packets of the most critical monitoring systems or the safety systems are dropped. Overall, we should be aware that IP cameras are a point of threat. They must be separated from the mission critical network, or at least, if that's not possible, apply quality of service. Once people know that such a threat can exist, it's very easy to overcome. But you need to know that IP camera is a threat on its own, even if it's protected with firewalls and intrusion detection systems and so on. Thank you.